Hi, today we're going to talk about lattices of Lie groups acting on the complex projective space. The content of the talk is the following. We're going to talk about split solvable projective linear groups, the discontinuity region of these groups, and lastly, we are going to talk about the limit set. So to start the talk, we recall the following definition about a complex Kleinian group. We are interested in these groups. These are discrete subgroups gamma of this group N+1 C. And one such subgroup is complex Kleinian if there is a non-empty and gamma invariant open set omega of projective space where gamma acts properly and discontinuously. We say that omega is a discontinuity region for the action of gamma. Now, what this means is the following. Recall, if we have a matrix or a pair of matrices A and B, both invertible matrices, we say that these matrices are equivalent if there exists a scalar, not zero, such that A equals lambda B. So the set of equivalence classes of these matrices, it's a group, or it has the structure of a group. This group is N+1 C. One element of this group acts in a natural way on projective space. So if we have this element of N+1 C, and we have this projective vectors bracket set, then the action of A, bracket A on set, is just the projective class of A set. Okay, so with this remark, now we have this definition of complex Kleinian group and of discontinuity region. We have a few more definitions. This one is the definition of hyperbolic toral automorphism. So what is a hyperbolic toral automorphism is the following. We have this integer matrix B with determinant 1, and this is called hyperbolic toral if no eigenvalue of B is of unit length on the complex numbers. If we have this hyperbolic toral automorphism, we are going to define this group gamma tilde B. And gamma tilde B is going to be defined as follows. Is the set of all the matrices in N+1 set such that an element of gamma tilde B is a matrix like this one, where K is an integer and B is a column vector itself, it's a column vector of integers. And this is the definition of gamma tilde. So what we're interested is in the case where gamma, a subgroup of the projective special linear group, this N+1 C, admits a leaf which is conjugate to gamma tilde B. What we aim to show is that one such gamma is a complex Kleinian group. So this observation is going to simplify a bit the things that we're going to discuss. The observation is the following. If gamma prime is conjugate to gamma by this element, bracket sigma of N+1 C, then omega is a discontinuity region of gamma, that is, gamma acts properly and discontinuously on omega, if and only if sigma omega is a discontinuity region for gamma prime. So since we are assuming that gamma means this leaf conjugate to gamma tilde, by this observation, we can assume without loss of generality that gamma is the projection of gamma tilde B. Now we can use this observation to simplify the following calculations. So the next observation, if we have this point in projective space with homogeneous coordinates like these ones, this is a point of infinite isotropy by the action of gamma. This is basically because this element in this element projects to gamma such that when it acts in a vector in projective space with the last coordinate equal to 0, then this projective point is preserved by G. Which is the first claim. Secondly, the complement of this set of points is this open set U of projective space. And in this open set, we can define a chart. We can define this local diffeomorphism from U to Cn that sends a point with these coordinates, homogeneous coordinates, to this vector. During this talk, we always think of vectors as column vectors. And this phi defines a chart on Cn. So what we can see now is that if omega is gamma invariant and the action is properly discontinuous, then omega has to be a subset of this open set U. Hence, we can think of omega. We can map omega to the complex numbers, to Cn, to the complex space. We can look at the action of gamma on complex place in this way. It turns out that gamma tilde is isomorphic to a semi-direct product of set n and set, the integers, vectors of integers and the integer numbers. And that in U, the action of gamma is equivariant to this action on the complex space. So instead of thinking about matrices of equivalence classes of matrices acting on projective space, we can study this problem. We can study the problem of the action of this semi-direct product on Cn, where the action is this one. And the claim is that, well, okay, with this observation, now we have this claim. There is a matrix M, a real matrix M, such that one of the following two alternatives hold. Either B equals to the exponential of M, or B squared equals to the exponential of M. Okay, so we have two cases. In the first case, we assume that B is the exponential of this matrix, and we define this representation given this matrix M. We define this representation as A of t equals to the exponential of t times M. This is a representation of the real numbers in the space of invertible real matrices of size M times M. And with this representation, we can define this Lie group the Rn times the real numbers. And it turns out that gamma tilde b, which we know is isomorphic to this semi-direct product of integers, is a lattice of this group. And moreover, as in the previous slide, that we have this representation of the action on the complex space, we also know that this Lie group of real numbers Rn semi-direct product with R acts on complex space in this way, like this. So what we're going to do now is to study the action of this representation. Sorry, we're going to study this action, this action of this Lie group on Rn, and we're going to extend this to the complex space with the chart phi. We're going to pull this action back to projective space. So the first step is to consider the stable and unstable subspaces of this matrix M. If we think of M as a linear operator, then these subspaces are defined as the M invariant subspaces where these two inequalities hold. Actually, the stable subspace is defined in terms of the eigenspaces of the matrix M. So if we find a decomposition of M invariant subspaces determined by the eigenvalues of M, we can consider the eigenspaces of M where the eigenvalues have negative real part. These invariant subspaces which are determined by the eigenspaces of M, they are the stable subspace. The unstable subspace is defined similarly, but instead of the negative real part of the eigenvalues, we consider the invariant subspaces that are determined by the eigenvalues with positive real part. What we're going to do is to use this decomposition on the complex space. So we move to the composition of Cn in its real part, direct sum with this stable space and this unstable space of the imaginary part. If we have this decomposition of the complex space, then we can define these canonical projections onto the stable space and unstable space. And we're going to define these open sets U1 as Cn minus the kernel of the first projection, and this second open set U2, which is defined similarly, but instead of considering the kernel of the stable projection, we're going to consider the kernel of the unstable projection, the projection onto the unstable subspace. Okay, so we have this lemma. The lemma says that there is an inner product on the stable space, such that if we consider this sphere S, then the stable space minus the zero vector is diffeomorphic to this product. This lemma is a consequence of the theory of Lyapunov stability, and there is a similar lemma for the unstable subspace, basically because the unstable space of M is the stable space of minus M. Okay, we're not going to prove the lemma, but the idea is to prove it is the following. Once we construct this inner product with Lyapunov stability theory, we can show that if this is the stable space, then each trajectory on the stable space like this one, intersects exactly once this sphere. From this simple observation, we can show that there is this diffeomorphism between this space of a sphere times these R real numbers to the stable space -0. Once we got this diffeomorphism, we can extend the proposition a little bit. I mean, we can extend the argument a little bit to prove this proposition. If we denote by GA this Lie group, the semi-direct product with respect to the real numbers and the representation A, then each one of the sets that we have already defined, UI, is diffeomorphic to a product like this one, where Xi is the product of a sphere and Euclidean space. And in this space, the action can be described as follows. If we have this H on the Lie group, and we have this pair here, then we know that UI is diffeomorphic to this product. And the action is simpler. I mean, it's equivariant to something simpler, because the action turns out just to be a left translation of the first factor of this product. H acts on this pair as HG X. So we can describe the orbits of this G action, right? The orbit space of the action is going to be basically Xi, and Xi is the product of something which is simpler. It's a sphere and Euclidean space. So this happens on the complex plane, on the complex space. But if we recall that we have this chart phi, then we can move to the projective space. We can move back to the projective space again. If we define this representation, rho A, like this, then the image of this representation is a Lie subgroup of this group of matrices of determinant 1. And we can project this image onto a Lie group which is itself a subgroup of PSLN plus 1R. And this group G acts properly and freely on the prime edge of UI. We define this set omega I as the prime edge of UI, and since phi is a chart which, and the action of gamma is the action of this group is equivariant to the action that we have already considered on CN. So we have these observations, and with these observations, we can prove this corollary. Gamma acts properly and discontinuously and freely on omega I, because gamma is a lattice of G. The first claim is because gamma is a lattice. And GA acts properly and freely. The second claim is similar. The orbit space of the action of G on omega I is a smooth manifold which is itself diffeomorphic to the product of a sphere and Euclidean space. Because we already know this property on the complex plane, on the complex space, sorry. Finally, the quotient space of the gamma action on omega I is a smooth manifold such that if we project this quotient onto the orbit space of G, then what we obtain is a trivial fiber bundle with fibers like this homogeneous space of G of equivalence classes of the gamma action on G. And this is basically because we know that omega I itself is diffeomorphic to the product, to a product. So we know that omega I is diffeomorphic to the product of the group, this Lie group GA, times something which is basically the product, which is diffeomorphic to the product of a sphere and Euclidean space. We also note that the action, the gamma action, is equivalent to an action that affects only to the first factor of this product. And from these observations, we obtain the third claim in the corollary. This is with regards to the first case. For the second case, we, instead of knowing that B is the exponential of M, of a matrix, real matrix M, what we know is that B squared is the exponential of this real matrix M. We define the following group. We define G tilde like this, and the projection of G tilde onto PSLN into PSLN N+1 C. Then it turns out that gamma is a lattice of G, and if we denote by G naught the connected component of the identity in G, then G naught admit a leaves to the image of this representation that we considered in the first case. Then, moreover, by the definition of G tilde, we know that G tilde is generated by this group G tilde naught, and by this extra matrix in SLN N+1 set. Okay, so we already know that there are invariant G naught invariant subspaces omega I on projective space, on the projective space. This comes from the first case, but if we recall that how we define these sets omega I, these sets were defined in terms of the invariant subspaces of the matrix M. Well, no, these spaces were defined in terms of the invariant subspaces of the matrix M, which basically are the invariant subspaces with respect to the matrix B squared. I mean, if N has a subspace eigenspace which corresponds to an eigenvalue with negative real part, then that same eigensubspace is an eigensubspace for B squared, where the eigenvalue of B squared is it has a norm less than a unit. What I mean is this. If lambda is an eigenvalue of M such that the real part of lambda is negative, that means that x lambda is an eigenvalue of B squared such that the modulus of x lambda is smaller than 1. But on the other hand, B also has an eigenvalue of modulus smaller than 1 in the same eigenspace. And likewise, if the real part of lambda is positive, then x lambda is an eigenvalue of B squared of modulus greater than 1. B also has an eigenspace with an eigenvalue of modulus greater than 1 at the same eigenspace, but for an eigenvalue of modulus greater than 1. So what I'm trying to say is that both B and B squared have the same stable and unstable subspaces. And what this means is that omega I is not only G not invariant, but it's also G invariant. With this observation, we arrive at the following proposition. If gamma admits a leaf conjugate in N+1 C to gamma tilde, where B is hyperbolic toral, and B squared is the exponential of some real matrix M, then there exists a Lie group G such that gamma is a lattice of G, and there are two open G invariant sets omega I in the projective space, such that gamma acts properly and discontinuously and freely on each of these open sets. And as in the first case, the quotient space is a smooth manifold. The quotient space of gamma, of omega I by gamma, by the action of gamma. At the same time, the orbit space of omega I by the action of G is homotopy equivalent to a real projective space, and the projection map is a fiber bundle with fibers, this quotient. Okay, so in both cases, in the first and the second case, the discontinuity regions omega I are maximal in the sense that if there is another open set of projective space, of the projective space, which is gamma invariant, then omega has to be contained in some of these sets omega. And this is the first remark. The second remark is that the conclusion of both propositions, the first case and the second case, also work for Lie subgroups of PSL N+1 C, which admit a leaf conjugate to the image of this representation, regardless of the lattice. What I mean is that in the proof of the propositions, in the formal proof of the propositions, it's not so important the existence of the lattice. The argument of the proof can also be applied to smooth Lie groups. For a smooth Lie group that admits a leaf conjugate to this group, it's also true that there is an open maximal invariant set where G acts properly. That's also holds. The orbit space of the G action is also, in the first case, diffeomorphic to the product of a sphere and Euclidean space, and in the second case, it's also homotopy equivalent to projective space. That's independent of the lattice. That's what I mean in the second remark. Finally, we address the question of the limit set. By definition, we say that lambda is the limit set of the action of gamma for this lambda, which is the complement of the two maximal sets that we found on projective space. And the proposition is the following. If gamma has the same hypothesis that in the previous propositions, it means a leaf conjugate to gamma tilde for some hyperbolic toral automorphism B, then we can prove that the set of points with infinite isotropy in projective space is dense in the limit set lambda, and that for almost any point in lambda, which at the same time is in the real projective space, the gamma orbit of this point is dense in this space, in the intersection of the limit set and the real projective space. The idea of the proof is the following. The first step is a fact. We know that a hyperbolic toral automorphism induces an action of the N torus. And we also know, I mean, this is known, that for almost any point in the torus, the orbit of this action is dense. What we have to do, what we do is basically unwrap this action on the plane, on Rn. We know that the complement, if we use a chart, the chart phi, we know that a point set in the complex space in Cn is in the limit set lambda if and only if this point is in both the kernel of the canonical projection onto the stable space and the kernel of the projection onto the unstable space. Since set is in both kernels, set is actually a real vector. Then the gamma action on the intersection of lambda, the limit set, and u will be equivariant to the action of this group of integers on Rn. But we know that for hyperbolic toral automorphisms, this action is dense in the torus, but we are adding an arbitrary vector b in Cn. So basically what we can do is we can unwrap the action on the torus and prove the claims about the limit set on this chart. That's what we do in the formal proof. But okay, so in case you wonder how is the formal argument for all of the claims on this small talk, I would like to refer you to this preprint where you can find more details about what we have covered today. So that's it. Thank you so much for your attention, and bye-bye.